Now, okay, we are going to introduce another equation. We have a lot of equations for this part. The equation called the conservation of the linear momentum. Okay, you can compare this with the conservation of the energy. The conservation of the linear momentum says that for some process, the momentum change can be 0. Okay, if that's the case, delta P equals to 0. So that means initial momentum equals to the final momentum. That will give you some equation to calculate it. But of course, the most important thing, okay, in fact, the most important thing when you use this equation is not the form of the equation itself, whatever conservation law. It's the condition to use that equation. When you can use a particular equation, like before, we have to think about when you can use the mechanical energy conservation, when you can use the total energy conservation. Okay. And the condition for the momentum conservation, you can see that since delta P equals to impulse J. So if we require delta P equals to 0, so that means the impulse acted on the system has to be 0. And impulse equals to, roughly speaking, equals to the force multiplied by time interval. Of course, time interval cannot be 0. Any process have to take some time. Okay, we don't have process actually happen as in no time. Okay, so delta T cannot be 0. So to make J equals to 0, the only way is to make the external force equals to 0. So that gives you the condition for the momentum conservation. The net external force acted on the system has to be 0. Okay, this is a very strong condition. It's very hard to make 0 force for object. Okay, like you always have the resistance. If you can, even you can put it in the vacuum. Okay, you may still have some distance from faraway place, like the gravitation. Okay, unless you can put it in a remote place in the universe which is far away from all the stars, it's hard to make the 0 external force for your object. But momentum conservation is actually very, very useful because we have the approximate condition to make the momentum conservation. So the momentum, in many cases, is approximately conserved. That's all. In fact, we only consider those kind of situations. When the external force is much, much smaller than the internal force, in that case, the external force can be ignored compared with the internal force, right? Like if you have some internal force like 10,000 Newton, and you give even a quite large internal force 100. But 100 Newton compared with this internal force is nothing. All the behavior will dominate it by the internal force. So in that case, you can ignore it. Then you have the momentum conservation. Okay, for example, explosion and collision process. For this process, you can think about the momentum is conserved. So whenever we talk about explosion and collision, you automatically realize that the momentum is conserved. And of course, you can see why I say it's very important. The explosion process and collision process are very important in our life, especially for the military purpose, right? Okay. They always, when they design the new arms, it's always involved with explosion or collision.